let's take a look at more examples. So in this example, we want to find the limit of the following function. The function is defined as a piecewise defined function. It means that on some part of the domain, it follows some definition. In some other parts of the domain, we have to follow a different definition. So when x is less than 2, we define the function, we define y values to follow x squared plus 1. When x is, however, greater than 2, then the y values actually follow a linear pattern, x minus 1. We're interested in finding the limit of this function while x goes to the boundary or 2. What is the limit of this function? Well, to find the limit of the function, recall that we need to find the limit while x goes to 2, x goes to c from the left, and find the limit of the function while x goes to 2 from right-hand side. If these two y values are the same, we say that, hey, the limit of the function is equal to that fixed value. Otherwise, we say that, hey, the function doesn't have a limit. Okay, perfect. When x approaches 2 from left-hand side, it means that we are working with numbers less than 2. X is less than 2. It means that we are getting closer and closer to 2 from left-hand side. When x is greater than 2, it means that we are getting closer and closer to 2 from numbers that are greater than 2. So x goes to 2 from the right-hand side. This helps us to identify which part of the function we should be using. X goes to 2 from left-hand side. The definition of y value on the left-hand side is a quadratic definition, x squared plus 1. So here you have the limit of x squared plus 1, and your x is getting closer and closer to 2 from left-hand side. Well, you stop here and you say that, hey, I have a quadratic expression. This is a nice function. I find the limit by direct substitution. So 2 raised to 2 plus 1 is equal to 4 plus 1 or 5. So if I go to 2, if I approach 2 from left-hand side, the y value is 5. What if I approach 2 from right-hand side? In this case, we have to follow the linear pattern for the y value. It is equal to the limit of x minus 1, and x approaches to 2 from the right-hand side. Again, you start analyzing this, and you say that since we have a linear expression, this is a nice function. The limit can be found by using direct substitution. Substitution 2 minus 1 is equal to 1. Sorry, I wrote down, yes, here. 1. So now you try to compare these two values. Your y value is 5, and your y value is equal to 1. Are they equal to each other? You say that since 5 is not equal to 1, it means that this function doesn't have a limit when x approaches 2. So our function has no limit when x approaches 2. Some functions are well-behaved functions, some other functions not so much. Another example for you. This example says, find the limit of x squared minus 4 divided by x minus 2, x squared minus 4 divided by x minus 2 as x approaches to 2. Well, what type of function do they have here? Here we have a quadratic expression on the numerator. We have a linear expression on the denominator, and it's a division between these two. It means that you have a quotient or rational expression. Well, what is the domain? The domain, when you have a rational expression, is equal to the set of all x values such that the denominator is never 0. X minus 2 is not 0. By adding 2 to both sides, you see x cannot be 2. So you might say that, hey, but we are finding the limit as x approaches to 2. You're saying that we have to exclude 2 from the domain. Well, in this case, we have to simplify the function first, and then we're going to talk about x equals to 2, which is actually a value that we're going to talk about for the graph of the specific types of function when we are finding the limit as x approaches to a value which is not in the domain. Just take a look at this expression. We can simplify this expression by using the difference of x squared minus 4, which can be written as x minus 2 times x plus 2. The difference between squares can be separated into their sum and their addition and subtraction. So on the denominator, you have x minus 2, and your x approaches to 2. Okay, here you can cancel out x minus 2 and x minus 2. What is left? We're left with the limit of x plus 2 and x approaches to 2. What do we have here? We simplified this rational expression into a linear expression, which is a form of a polynomial. It is a nice function. You can just use direct substitution to actually calculate this. You get 2 plus 2, which is equal to 4. Let's take a look at the graph using Desmos and see what's the behavior of this graph. So our function on the numerator, we have x squared minus 4 divided by x minus 2. Take a look at the graph of the function. After simplifying the graph, the function, we get a linear expression, and take a look at your board. After simplifying this rational expression, we end up with a line, a nice line, x plus 2, and Desmos gives us the graph as we can see it here.